Hi and welcome to this video on combining uncertainties for IB physics. To combine uncertainties, we have to use 4 key rules, and what I thought I'd do is just talk through those rules very briefly and then show you a couple of examples on how we apply them. So don't worry about the beginning, this is a bit dry. To be honest, the topic of uncertainties is dry throughout. However, we will be able to apply it to different situations, and it's a really key skill in understanding how experiments work. So, those 4 rules, the first one is fairly simple. When we're taking two numbers and we're adding or subtracting, and we want to find the uncertainty in the final value, all we do is add together their absolute uncertainties. If instead of adding or subtracting, we are multiplying or dividing, then instead of adding together absolute uncertainties, we add together percentage uncertainties to get the percentage uncertainty in the final value. Regardless of addition or division, multiplication or subtraction, when we are presenting our uncertainties, we always present to one significant figure in the final presentation. And finally, that uncertainty must come in the least significant digit of the value that we are presenting. As I've said, I think this is much easier if we consider this through a couple of examples, and that's what's going to come just now. First up, adding and subtraction. Now, I'm just going to repeat our rule there, number 1. When we add or subtract two numbers, we add together their absolute uncertainties to find the absolute uncertainty in the final value. Let's take two numbers, and these are going to be the numbers we use for all 4 examples here, just to show how we work with our uncertainties. A, 3.2 plus minus 0.3, and B, 2.5 plus minus 0.5 centimeters. Well, if we're adding these things together, it's nice and easy. C, for example, is A plus B, it's just the sum of the two numbers, 5.7. If we want to now know the uncertainty in C, all we have to do is add together the uncertainties in A and B. So delta C, that's our uncertainty in C, is just delta A plus delta B. We know those two values from the original question, and so we add them together and we get 0.8. And so if we're presenting C, we present it in this way, 5.7 plus minus 0.8. That's the value plus minus the uncertainty. Subtraction follows exactly the same rule. Again, we've got the same two numbers, but this time I'm going to define D is just the difference between those two. I've got 3.2 minus 2.5, which is 0.7. What about their uncertainties? Well, notice in the rule number 1, the uncertainties follow the same pattern. So even though I'm subtracting my two numbers, I must add together the uncertainties. And so actually, the uncertainty in D is exactly the same as the uncertainty in C. It's 0.8 centimeters. And we add that into our final presentation to show that D is 0.7 plus minus 0.8. Now I've chosen this example because it shows something slightly weird about uncertainties. Here, you notice we've actually got a really, really large percentage uncertainty in D. If you notice here, my uncertainty is actually greater than the value itself. So we've got a percentage uncertainty of greater than 100%. That is just one of the features of using uncertainties. We're not breaking any rules by doing that. So please remember that when you are subtracting, you still must add together the uncertainties as opposed to subtracting them. Quick check at the end for rule number 3. Our uncertainties should be given to one significant figure. Absolutely, we've got one significant figure in our uncertainty here, and we've got one significant figure here. And now notice that we've got the same number of significant figures in my value and one more in my value for C. That's absolutely fine. More on significant figures when we look at multiplication and division. Let's go to division first because as you'll see, the example gets a little bit more complicated for multiplication due to significant figures. Again, we're doing exactly the same numbers, A, but this time we're going to divide it by B. I'm going to define F as A divided by B, and I get 3.2 divided by 2.5, 1.3. Now notice I'm sticking with two significant figures there in my answer because the original values were given to two significant figures. We then need to add together the percentage uncertainties. Now this is the tricky point. Remember, when we multiply or divide numbers, their percentage uncertainties add together. So in this case, I get my percentage uncertainty in F is the percentage uncertainty in A plus the percentage uncertainty in B. I take 0.3 divided by 3.2, I take 0.5 divided by 2.5, and I get 0.294. Now remember, that is the percentage uncertainty in F, and so in order to get the absolute uncertainty in F, I need to multiply my value of F by that 0.294. And I calculated that before 1.3, and I get a 0.38. So if I wanted to just write this down in terms of presenting my data, I would have F, apologies for the typo there, F equal to 1.3 plus minus 0.38. However, we have to observe our rules about uncertainties, in that the uncertainty should be given to one significant figure. So instead of having 0.38, I'm going to have to go for 1.3 plus minus 0.4. So when you are doing these questions, I would advise that you write down the uncertainty to a great number of significant figures and then convert to one significant figure if you have to. This will show that you are thinking about the different rules and how they apply. Last one then, multiplication. Again, same numbers. We're going to multiply, and this time we'll go for E equal to A times B. Now when we chose these numbers, you might find you get 8 on your calculator. Really it's 8.0 because we're taking two numbers with two significant figures, remembering our rules that if you present an answer, it must be to the minimum number of significant figures used in the calculation. Again, when we multiply our numbers, we're going to have to add together the percentage uncertainties. And again, look, we have delta E divided by E, same as before with our division. The percentage uncertainty in the division and the multiplication is the same because there's no discrimination between the two. Once more, I'm going to have to multiply my value of E by the percentage uncertainty in order to get the uncertainty itself. So I'm left with an answer which to a physicist is not very satisfactory. Look at this first line here, E equal to 8.0 plus 2.35. We then need to apply our rules. We need to apply our first rule 3, which is the uncertainty must be given to one significant figure. Now 2.35 is given to one significant figure is just 2. Okay, we've got our 2 as our number is closer to 2 than it is to 3, giving it to giving it to one significant figure gives me the answer of 2. Now notice again that we have to apply our rule 4, which is that the uncertainty must come in the least significant digit of the value itself. If you notice here, we have 3 significant figures and 2. We've reduced it down down to one significant figure. However, the least significant digit in our value is 8. And so therefore, these two values must match up in terms of the significant digits. This kind of conversion is a real tricky part because you're having to think about multiple different factors. Firstly, how many significant figures I'm allowed to give my uncertainty to, and secondly, what the least significant digit of the value is. If, for example, we had 18 plus minus 2, that would be fine because the least significant digit of 18 is 8, and therefore the significant digits would match up. However, in this case, because we've got 8.0, this 0 becomes more significant than the 8. It is the most significant digit. We have to lose the 0 in order to present our answer to the sufficient number of significant figures. I'm aware that is a lot of information, so I do encourage you to check your answers, compare them to mine, and see if you have any questions. I'm more than happy to help you looking through this. Uncertainty analysis is a really tricky, really nasty thing to have to do, but once you get the hang of it, you will find it goes very, very smoothly. Hope you enjoyed that video, and let me know if there's anything else I can make clearer.